Some logarithmic expressions can't be evaluated any way other than with a calculator. They don't have a exponent form that you can rewrite it in and be able to evaluate it. Now, on a calculator, we only have two log buttons. There's the log button, which is base 10, and then we have the ln button, which is base e, which means in order for us to be able to use a calculator, we have to have our logarithm written in terms of one of those bases. And we can see in this set of examples we're going to go through in a moment, we don't have that as of yet. So we need to be able to rewrite these expressions in terms of either a base 10 log or a base e log, the natural log. And for that, we have the change of base formula. And so the change of base formula has the pattern as follows. So if we have a base b for a logarithm and we want to change it to something else, so in this case base a, which would be either base 10 or base e, depending on what we prefer. So whatever is the input into the logarithm, that's going to go up into the top of the new expression. So we now have a new log base a with the input into the logarithm going up top in the numerator. And then in the denominator of this new expression, you can see that we're taking the log base a, so our new base, of the original base b. So let's put this change of base formula into practice here. So for starters, before we even get to that, it's worth it to try to come up with an expectation as to what our answer should look like. So for example, if I set this equal to x and I rewrite this as an exponential, I can rewrite it as 3 to the x equals 24. So the base of the log becomes the base of my exponential. What it equals, x, becomes my exponent, and then the input to the logarithm becomes the output of the exponential. And so I know that 3 to the second equals 9, and I know that 3 to the third equals 27. So that means my exponent x here, or what the value of this expression should turn out to be, is somewhere between 2 and 3. A little bit closer to 3, since 24 is a little bit closer to 27 than it is to 9. So this sets up an expectation for me that my answer should be in that range. So now let's rewrite this using the change of base so we can actually use a calculator to evaluate it. So using the pattern, we're going to use log base 10. So we're going to use the base 10 logarithm here. So we've got log base 10 of 24. So the input goes up to the top. And then in the denominator, we're going to have log of the original base, 3. And so now we can do this on our calculator. So I'm going to type in log of 24, and so we get an answer of 1.308 if we round off to 3 decimal places. In the denominator then, we're going to do log of 3, so we hit the log button of 3, we get 0.477, and so now I just need to divide those two results, and so we get a result of 2.741. Which, again, if we go back to what our kind of predicted expectation was, that definitely satisfies what we expected. Somewhere between 2 and 3, probably closer to 3 than 2. 2.741 definitely satisfies that. For the next one, if we do the same sort of expectation setting, so again, we can rewrite this in exponential form. So 4 to the x equals 72. And so we know 4 to the first is 4, 4 to the second is 16, 4 to the third is 64. 72 is a little bit bigger than 64, so we can expect that x should be a little bit bigger than 3, so a little bit larger number than 3. 4 to the fourth would be 256, so way bigger. So now that we've generated that expectation, let's rewrite it using the change of base. This time we'll use natural logs. Again, we can use either one. We're just choosing to use these because they're calculator friendly. So we can rewrite it. Natural log of, so the input goes into the numerator, so natural log of 72 over the natural log of the base, so the natural log of 4. And so now on our calculator, natural log of 72 is 4.277. And then if we push buttons to get natural log of 4, we get 1.386. And so then if we divide those two, we get a result of 3.085, which again matches up with our expectations when we kind of made our estimate at the very outset. And for our last one, again, if we do the same sort of expectation setting, so set it up so it's 8 to the x equals 80. Well, 8 to the first is 8, 8 to the second is 64, 8 to the third would be much larger, 512. So we know that x should be a little bit bigger than 2 when we're all said and done. So this time we'll go back to using our base 10 logs. Again, as long as we use the same log for the top and the bottom, doesn't matter if we use the natural logs or the base 10 logs as we did on the previous two examples. So this time we'll just go back to the base 10. So just the regular log button. So log of the numerator, 80, is the input. Log of the base 8 in the denominator. And so now log of 80, if we use a calculator, we get 1.903. Log of 8 is going to be 0.903. And so then if we divide those two results, we get 2.107 as the value of our expression here. And again, going back to what our predicted value was, a little bit bigger than 2, this definitely satisfies that.